Hey guys, today we're going to start our study of astronomical principles with Kepler's laws. Now, Kepler had more than three laws, but we are only concerned with three of them in this class. We're going to learn about the first and second laws in some detail, and I do want you to understand those or know those to pretty much everything there is to know about them. We're also going to look at the third law, Kepler's third law, but just the concept of it. Kepler's third law is purely mathematical, and the math is just a pain in the neck to do, and I'm not going to make you do the math for it. But I do want you to know what it covers and what it describes. Let's start off here with a story. Our story begins with a guy named Tycho Brahe, which is a cool name if there ever was one. And if you look him up on Wikipedia, they'll say he was the great Danish astronomer, and this is a portrait of him. Tycho Brahe was a strange guy, and we probably would not remember him but for Kepler, who we're really interested in today. But the story of Brahe is an odd one. Tycho Brahe was a Danish nobleman. He owned an island all to himself, lived back in the 1500s, that time frame. And he ran his estate and his lands like a little Hitler. He was not a good guy. He had no regard really for anyone other than himself, and he considered the lives of the peasants that lived on his land as pretty much immaterial. He could do whatever he wanted with them. He was probably crazy. As you can see in this portrait, his nose looks kind of weird. Well, why does his nose look so weird? When he was a teenager, probably high school age, 17, 18, 19 years old or so, he challenged another nobleman to a duel, sword fight to the death, and he lost. And rather than kill him, his opponent chose to cut off Tycho's nose. So Tycho went through life with a silver nose, which he would use to cover the holes in his face. And supposedly he'd wear a gold nose on special occasions. I don't know if that was true or not, but yes, he went through life with a silver nose. Now, despite this defeat in this duel when he was a teenager, Tycho believed that he was the reincarnation of the god Mars. I'm not making this up. He believed that he was the god Mars put here on Earth, which presumably is why he had control of his estate and he was a nobleman and all that. Now, because he considered himself the god Mars on Earth, which was the god of war, he was very interested in the position of the planet Mars in the sky. So he used his considerable wealth to to have made for him the best astronomical observation equipment that could be created with the technology of that day. And he had it set up on his estate. So he could measure very precisely the position of the planet Mars in the sky, how far away it was from the North Star, how high up it was above the horizon, and exactly what time he was taking these observations every night. And for decades, he would go out every night and very carefully and precisely measure the position of the planet Mars in the sky. And when he was out of town or had something else to do, he would have servants go out and take these observations. And he would do it every night that Mars was visible for decades. He was also interested in the motion of the other planets because he considered them his brothers and sisters. So he gathered data on Saturn and Jupiter and Mercury and Venus and all the other planets as best he could. But the most complete data was for the planet Mars. Now, he considered these things his own personal information, privately held information, but he really didn't know what to do with it other than just having, these books full of numbers. Well, that's where Johann Kepler comes into the story. Johann Kepler was a priest, a Catholic priest. And at this time in history, if you wanted to have some sort of advanced education, you had to enter the clergy and go to religious schools. So he was not the kind of priest who ran a parish church and had a congregation. He would actually travel the countryside. Johann Kepler did after he got this education. And he made his living as an astrologer. Now, as you probably know, an astrologer is somebody who tries to predict somebody's future based on the position of the planets at the moment of their birth. There's nothing to this, but it was believed at the time. And this was not considered occult or anti-religious at the time. This was considered reasonable. So Johann Kepler knew how to calculate the position of the planets in the sky if all you gave him was your birthday. He could kind of run the clock backwards and figure out where the planets were, so he could capture your astrological forecast. So Kepler had the mathematical chops to make sense of this massive data that Tycho Brahe did. So Kepler spent years crunching numbers that Tycho had gathered. Now, we remember Tycho as the great Danish astronomer because he recorded this data and he made these observations. But Tycho didn't really do anything with it, and we wouldn't remember Tycho if not for Kepler, because Kepler found the patterns in that data. So when Tycho died eventually, he declared in his will that all of this data should be burned because it was his personal love letters to himself, if you will. That was nobody's business but his own. But for some strange reason, instead of being burned, all those books wound up in Kepler's saddlebags when he rode out of town. So Kepler preserved this data and then spent basically the rest of his life analyzing it. Now, Kepler found many patterns in the data. There were 3 of his laws that we remember to this day because there was actually something to them. There are actually more patterns that he found, but some of them were just coincidences. Anyway, first law, you got to know this. Kepler found that the shape of a planet's orbit is an ellipse. Now, before this time, it was believed that the orbits of the planets were perfect circles because a circle is a perfect shape with no beginning and no end. It's eternal and therefore divine and perfect. So the shapes of the orbits must be circles. Kepler, by crunching the numbers, figured out, nope, not so much. It's actually an ellipse. And I'll explain what an ellipse is in just a moment. The second part of this is that the sun is at one focus of the ellipse. So to make sense of this, we got to see what an ellipse is. So let me show this. Let's see, we'll go to this and this. Okay, so this is a video or a piece of a video that I'm going to show you here. And I'm going to mute that so this distracts me. Okay, so what he's done is he's put 2 nails in a board and he has a loop of string that he's put around these 2 nails, and then there's enough slack that it goes out to farther away. Now, it turns out that there's a few ways you can make an ellipse, but the way he's doing it is it turns out if you take the distance from one nail to the other nail and then to a point, at some point, some distance away, and then back to the first nail. So this total distance from one nail to the other nail to the pencil, back to the first nail. That total distance, you keep that constant and you plot the group of points that all satisfy that requirement, that from A to B to C adds up to a constant number. So what he's doing, he's basically putting his pencil here and drawing this oval, and it goes all the way around. All the way around, and there it is. That shape, that oval, is by definition an ellipse. And the place, so it's sort of like an oval, but it's not just any oval, it's a specific oval that has this property. So that's an ellipse. Now, the point where the 2 nails are, those are called the focuses. So this is one focus, this is the other focus, and that's what describes the ellipse, is the distance between those and the distance out to the ellipse itself. Okay, so the places where he put the nails, those are called the focuses. And what Kepler's first law says is that the shape of a planet's orbit, like the Earth going around the sun or Mars going around the sun, that's an ellipse. And the sun is at one focus of the ellipse, meaning that you have the 2 nails that you use to create this ellipse. The sun is at one of those focuses. And then the Earth, or whatever planet you're interested in, is following this elliptical orbit. Now, the orbits of the planets in the solar system are much closer to circles. They're not this squashed. This is very, very exaggerated. They're nearly circular, but not quite. And Kepler was able to show that they are actually ellipses. And the sun, that's what this yellow one is, at one focus of the ellipse. Now, you may be wondering what's at the other focus of the ellipse. And the answer is nothing. There's nothing there. It's just the path that the planet takes is an ellipse, and one of the focuses has the sun, and the other one is nothing. And at the time, this was seen as a reason not to believe Kepler, because how can a planet be orbiting nothing? So yeah, it was rejected, even though the math was there. But the people making this criticism didn't understand the math. Anyway, so you need to know the orbit of the planets is an ellipse, and the sun is at one focus is one focus of the ellipse. And it's probably useful to remember that there's nothing at the other focus of the ellipse. Okay, second law. The second law, this is going to sound weird at first, but it'll make sense in a moment. A planet sweeps out equal areas of its orbit in equal times. That's the second law. Now, what do we mean by this? This works a lot better in class, but we've made this to make it work. Okay, so here we have our ellipse. The sun is at one focus of an ellipse. Now, as you probably know, the planet is going to go faster when it's close to the sun and slower when it's farther away, because the force of gravity is stronger when you're close to the sun and weaker when it's farther away. Now, if you watch the planet for a period of time, like 2 days when it's out here, it's going slow so it doesn't go very far. And if you want to, you can draw a line from where the planet is at the beginning of the time, at the end of the time, and draw lines back to the sun. And it kind of makes a pizza slice, okay? And if you do the same thing when the planet is closer to the sun, it's going faster, so these 2 points are farther away. And you have a shorter, faster pizza slice, okay? So long, skinny pizza slice when the planet's far away, short, fat pizza slice when the planet is close to the sun. What the second law says is that the area of this pizza slice is the same as the area of this pizza slice. The area swept out in a given period of time is always the same. Strange thing, but that's how it is. And I have no idea how Kepler figured this out, just looking at basically a phone book full of numbers, but the guy was brilliant. So what are you going to do? Okay, so you need to know this. I find it easiest to remember as an image, as a picture. It's the idea of the pizza slices being the same size, and that the edge of the pizza slice is defined by how much time it takes for the planet to travel. And in words, it says, yeah, planet sweeps out equal areas of its orbit in equal time. Great. Okay, that brings us to the third law. The third law is a relationship between the period of an orbit, in other words, the time it takes for the planet to go all the way around one time, and the radius of the orbit, in other words, how far it is from the sun. Technically, it's the semi-major axis of the ellipse, but if we think of the planet's orbits as being pretty darn close to circular, we're talking about the radius of the orbit. And Kepler was able to find a pattern between how long it takes to go around and how far it is from the sun. And this relationship he found is the same for every planet in the solar system. Okay, so if you take the time that it takes for Earth to go around the sun in, say, days, and square that number, and then take the distance from the Earth to the sun in miles and cube that number, and take the time squared divided by the radius cubed, you're going to get a number. When you do that math, you're going to get a number. And then if you do the same thing for Mars, take the period of its orbit and the radius of its orbit and treat it the same way and do the math, you'll get the same number. You get the same number when you do it for Earth as you do for Mars. And if you do it for Jupiter, you get the same number. If you do it for Saturn, you get the same number. So he found a relationship between the period of the orbit and the radius of the orbit. And that's all you need to know. You need to know that it's a relationship between the period of the orbit, the time to go around, and the radius of the orbit. You do not have to actually be able to do the math and crunch the numbers. That's a pain in the neck and it doesn't contribute much. Let's see, that's what we have. So we learned about Kepler's first law, second law, and a little bit about the third law. We learned how to make an ellipse, and we learned a little bit about this weirdo Tycho Brahe and this brilliant guy Kepler. Now, you may be wondering, why do we care about this stuff? And the reason we care about this stuff is because when Isaac Newton came along, he could derive Kepler's laws from his own. Newton said in a very rare moment of modesty that if I see far, it's because I stand on the shoulders of giants. And Kepler was one of those giants. Kepler crunched the numbers to show Newton that Newton was right about how the universe works.